Now that we've discussed series and parallel circuits, we can analyze circuits with both series and parallel branches, and they're called series parallel circuits. The technique for solving is we just go through each branch step by step and we find equivalent resistances using Req equals R1 plus R2 plus R3 ... for resistors in series. And we use R equivalent is 1 over R1 plus 1 over R2, and so on for resistors in parallel. Okay, so let's see an example of how we would analyze one of these series parallel circuits. Suppose we want to find R equivalent, and after that we want to find the current that goes through R7. So here's our circuit. We have a 12-volt source. Suppose we have a resistor here, and then there's a node here. The current can split up to, we'll call this resistor 2, resistor 3. This will be resistor 1. And then after that, let's put another resistor here. And after that, the current can split down this parallel network. Let's say we've got 2 resistors down this branch, and then it comes back to the source. All right, so I'm going to label this as R5. This branch here will have R6, R7, and let's just give these some arbitrary values, just since we're doing a practice problem. So let's let this be 2 ohms. This can be 4 ohms. Suppose this is 5 ohms. R4, 6. We'll let this be 3 ohms. Suppose this is 1 ohm and this is 4 ohms. Okay, so we're going to go through step by step, and we're going to basically simplify all of our parallel networks so that we can just break this down into one series circuit. Okay, so how I'm going to do that, I'm going to start with this parallel network of R2 and R3. So since R2 is in parallel with R3, we can replace this network here with the equivalent resistance. So I'll just call it R sub A, and to find that, I'm going to use my formula for finding equivalent resistance for resistors in parallel. So for this case, it'll be 1 over R2 plus 1 over R3. So that gives me 1 over 4 plus 1 over 5. So this is going to be 20 over 9 ohms. Now, I can do the same thing for this parallel network as well. But the thing about this one, it not only has R5, but down this branch it has R6 and R7 are in series. So we want to add these together to combine them in series first, take that result, and then combine it in parallel with R5. So let's do that. Since R6 and R7 are in series, I can find the equivalent resistance between those two. I'll just call it RB. That's going to be R6 plus R7. So that's 1 ohm plus 4 ohms. So RB is going to be a 5 ohm resistor. And now R5 is in parallel with RB, so I can find a new equivalent resistance. I'll just call it RC, and that'll be given by 1 over R5 plus 1 over RB, where RB is the equivalent resistance between 6 and 7, which were in series. Okay, great. So this is going to be 1 over R5, which is 3 ohm resistor. RB we found to be 5, so this will be 1 over 5. So this gives me 15 over 8 ohms. So at this point, I have replaced these parallel networks with just one resistor. So I can rewrite this whole thing as one resistor and this whole thing as one resistor. So my circuit now looks like this. Here's my 12-volt source. I still have R1. Then in place for that parallel network, I now have RA. And then I still have R4 here. And in place for the parallel network that was below that, I now have RC. And I just arbitrarily called them RA, RB, and RC, just so I could do my simplifications and keep them organized in my notes. But the good news is now I just have a simple series circuit. So since all these resistors are now in series, I can find R equivalent for this whole thing. So this is going to be the total resistance that's seen by the source. So our R equivalent for the entire series circuit here, series parallel circuit, will be given by just adding up R1 plus RA plus R4 plus RC. So for R numbers, this was R1 was 2, RA was 20 over 9, R4 was 6, and our RC was 15 over 8. So this ends up being, it's not really a nice number, but here it is. It's 871 over 72, which is about 12.1 ohms. Okay, so our equivalent is about 12.1 ohms. Once we have that, since we know that this is a 12-volt source, we can find the current that's being delivered to our circuit by the source, just by using Ohm's law. So, by Ohm's law, V equals IR. In our case, we have voltage of the source is equal to, I'll call it I coming from the source times R equivalent. So we know that our source is 12 volts. We want to find the current that's coming out of the source, and we know our R equivalent is 871 over 72. So this implies that the current being delivered by our power source is 864 over 871 amps. Okay, great. So now we have the current that's coming out of our source. Now, if we work backwards, so even though I have this written as a simplified series circuit with just one R equivalent, you guys know that this is actually this. And you also know that this is actually this. So if we work backwards, if we find this I source, we know that since these are in series, that this IS is what's going through all of these resistors. That means we can find the voltage drop at each one of these resistors. So let's do that. So using Ohm's law, we can find voltage at each resistor. So what would those be? Well, for V1, that's just going to be I source times R1. For VA, voltage drop across resistor A, we have current from the source times RA. And then at resistor 4, the voltage drop across resistor 4 is IS times R4. And at resistor C, the voltage drop across resistor C is IS times RC. Now, the one I'm really interested in is the voltage drop across this parallel network. And the reason why it was at the beginning of my problem, I was asked to find what is the current going through R7. Okay, so I'm interested in finding this current that's coming, that decides to take this branch. So if I can find the voltage drop across this RC, you guys know that this RC is actually this parallel network here. This is what we replaced with RC. So if we can find the voltage drop across RC, that will be the voltage drop across R5 and the voltage drop across R6 and R7 combined in series. So that's what we want to find next. So our VC is going to be our IS, which we found to be 864 over 871 amps. And then our RC value was 15 over 8 ohms. So this is going to give us 1620 over 871 in volts. And I'm keeping this in fraction form so I don't lose any precision by rounding my decimals. So now we have the voltage drop across RC. So here's my RC. My voltage drop VC, I now calculated what that is. I have a numerical value for that. So remember, this RC is R5 in parallel with R6 and R7. So that means that if the voltage drop across RC is VC, that makes VC go from here to here. So VC, the positive side of VC is on the top of this node. The negative side of VC is on the bottom of this node. Since these are all one node, that means that the voltage drop across R5 is also VC, and the voltage drop across R6 and R7 is also VC. Okay, so here we have our R6 and R7 we replaced with that RB, right? And we said that our RB was just 5 ohms because we just added our 1 ohm and our 4 ohm resistors together. So if we know that this is 5 ohms, we know the voltage drop across here is VC, we can find the current that takes this branch. The current that goes through R6 is the same current that goes through R7 since these are in series. So let's do that. We can say that VB is equal to the current that goes through the B branch times RB, and this implies that the current that goes through the B branch is equal to VC over 5 ohms. So our VC we found to be 1620 over 871, 1620 over 871, and we divide that by 5, and so our IB, which is our I7, so that's the current that goes through the resistor 7, is 1620 over 4355, which is about 0.372 amps. So that's 372 milliamps. And we're finished. So I just wanted to show you how we go through systematically and change first all the parallel branches to series, and then we can have a simple series circuit, and then we work backwards to find any currents or voltages that we are asked for at the specific resistors.